All right, I'm gonna spend the first part of today's lecture to go over the questions that were included on the exam 2 information. I think it's not gonna take the full 15 minutes. So what I'm going to do in the remaining time is if you guys have any questions, I'll stay until 12:50 to take those. And like I am recording this, so you should be able to find it later this afternoon on YouTube as well. So I will upload it to YouTube as soon as I have finished compiling and uploading video recording. All right. So what my plan is for each question, I'll first go over the rationale and a sample solution I have over here, and then let's run it together inside R and see what are some of the intermediate steps and objects we generate. All right, so let's get started with the first question. This question says that there is this sample skewness statistic denoted by square root of B1, right, given by this observed data of size n from some distribution. So this is going to be a question that's related to Monte Carlo inference or simulations, where it asks you to figure out what is the sampling distribution of this sample skewness statistic. Just as a quick note, when is this going to be useful? So a lot of the times you might be interested in testing the skewness of a distribution, right? So whenever you obtain samples from a distribution, you might be interested in finding out, is that distribution skewed or not? So it turns out that this sample skewness statistic is very useful in this kind of skewness tests, right? So let's get started with part A. In part A, you are asked to write a function in R that takes three things as inputs, right? Your sample size n, mu, and sigma squared. Essentially, n is the number of samples of x you get, and the mu and sigma square are the mean and population variance for that distribution of your x, right? So you know that the x is actually distributed with a mean of mu and a population variance of sigma squared following a normal distribution. So this function takes these three things as inputs, and it asks you to return the Monte Carlo estimates of the expectation and the standard error, which is essentially the standard deviation of square root of B1. Right? One thing you will need to decide yourself is how many Monte Carlo replications you're going to do. Right? Let's just say we are going to do a total of 10,000 Monte Carlo replications. The idea is that in each replication, we're going to generate a sample of size n from this normal distribution with mean mu and variance sigma squared. We compute the sample skewness, and then across the 10,000 replications, we take the average or the standard deviation, which gives us the two estimates we're interested in. So here's the code for part one. Here, the function, I name it as MCEst. It's for Monte Carlo estimation of some of the like the most famous properties of a statistic. Right? This function takes n, mu, and sigma squared as inputs, and it says that I'm going to create a placeholder, square root B1. Now it's a bunch of zeros, but later on I will replace it with the 10,000 replicates of the Monte Carlo simulated square root of B1. Right? In each replication, I'm going to first generate the data from a normal distribution with size n, mean mu, and standard deviation equals to the square root of the population variance. That should give you a sample of size n from this desired distribution. And then essentially what you do is using this random sample you have, which is a vector of length n, calculate the square root of B1. What you can do, what I do over here is calculating the numerator and the denominator separately, where the numerator is given by the average of the xi minus its mean raised to the power of 3, right? Essentially just spelling out the numerator over here. The denominator is given by the, essentially you can see that is the average square deviation between each point and the sample mean raised to the power of 2/3. Once you have those two, you know that the jth replicate of your sample skewness statistic is just the ratio between these two things. Right? Essentially, this part spells out how you transform the x samples you have into this statistic, sample skewness statistic. So you should end up with a total of 10,000 of them. And those are the 10,000 Monte Carlo replicates of your sample skewness statistic. To estimate the mean and the standard error, essentially just take the sample mean and the sample standard deviation. And then your function can return the vector containing these two things. So here's a little bit about the theoretical property of this. So if your data is actually generated, so if your axis comes from this normal distribution with mean 0 and standard deviation of what is 1 over here, right? For large n's, so as your sample size goes to infinity, this sample skewness statistic, when your samples actually follow this normal distribution, should have a mean that's very close to 0. Why? Because the normal distribution is not skewed, right? So the skewness should be close to 0. And the standard deviation or the standard error should be close to the square root of 6 over your sample size. So in this case, it's going to be close to square root of 6 over n equals to 100, right? So 6 over 100. If you plug in these arguments of n equals to 100 and mean of 0, standard deviation or population variance of 1, you can see that the Monte Carlo estimates that we get is actually quite close to what we would expect when mean is quite close to 0. Standard error, if you use R to compute what is the, say, square root of 6 over 100, that's something close to 0.24. And it turns out that it is quite close to what we get using the Monte Carlo estimates. So now let me quickly run the code so you get an idea of what each step is inside here. This MCF function, essentially you can see that it's going to take the arguments n, mu, and sigma squared, and then applying this, you get the two numbers that are close to what we would expect theoretically. All right. If you have any quick questions, please feel free to type it up in the chat box. Okay. If not, let's move on to part B. So part B is also related to Monte Carlo inference, but this time what you're trying to figure out is what is the chance that our skewness statistic falls outside some interval. So this time you're interested in estimating what's the chance that its absolute value exceeds some given constant W. How is this going to be useful? It's very useful when you're doing hypothesis testing, right? So let's say that you, on a observed sample, you observed a sample skewness statistic of, say, 1 point something, or just 1, right? You might be interested in figuring out what it will be a p-value for the skewness test. So if the underlying distribution is normal, which is symmetric, not skewed, then what is the chance that I observe a square root of b1 that's extreme or more extreme than what I calculated from the data I collected? So the idea of the second part is very similar to the first part, except that the kind of estimate you compute is going to be some sort of probability, right? I call this function MCPest. The arguments are quite similar to before: sample size, the data generating mean and variance, and some W, which is the constant that you will compare the absolute value of the sample skewness to. Right? This part is the same as before, which essentially in each of the Monte Carlo replications, over 10,000 replications, you're going to generate some data from this known distribution, so normal mu sigma squared, and then compute a Monte Carlo replicate of this sample skewness, right? You have a total of 10,000 of those simulated sample skewness where your x follow this normal distribution. And then to estimate that probability, you can compare each of those 10,000 square root of b1 to the constant w, right? And the proportion of times that the absolute value of square root of b1 exceeds this w can be given by the average of this true-false function, which is essentially the indicator function. is our simulated square root v1 greater than or equal to the W constant we specified. And then at the end, you return this estimated probability based on the proportions. This question asks you to test your function with sample size 100, mean of 0, variance of 1, and a W of 1. Right? What essentially it asks is when you have a sample of size 100, when your data comes from normal 0, 1, what is the chance that you observe a square root of b1, a skewness who has an absolute value exceeding W equals to 1? And you can see that here it's going to fluctuate a bit, but the output you get should be very small, meaning that if your data actually comes from the standard normal distribution, it's quite unlikely for you to get a value of the observed sample skewness that's greater than or equal to 1. All right, are there any questions about question 1? If not, let's move on to question 2, which is related to permutation tests. The first part of this question, I think it's a little bit tricky, right? But I thought it was a nice thought exercise for you to think about what we're actually doing in permutation tests. So let's take a look at this question. We have a data set where X has a sample size of 3, right? So 1.2, 2, and 3 are the 3 observed values we have. And Y has a sample size of, if I remember correctly, 10, right? So these are the Y values that you have observed. We're interested in using this set X and set Y to do a hypothesis test of identical distributions. Essentially, under the null hypothesis, we assume that both X and Y are uniformly distributed with the same range, so the same lower and upper bounds. The alternative hypothesis is that the range of Y, when Y follows uniform, is actually nested within the range of X. Essential idea that the minimum that generated the X data is something that's greater than what is the minimum that generated the Y data. Right? And the maximum that generated the X data is actually larger than the maximum that generated these 10 Y points. All right, so for this question, the test statistic we employ is going to be the range of the X sample. It's expressed as this order, the difference in order statistic over here. Essentially, when you have a 3 observed X's, you find out who's the maximum, who's the minimum, you take the difference between those two, and that gives you the range. If we expect the alternative hypothesis to be true, then what that would mean is that the range of X is going to be greater than the range of Y. So a larger value of T will support the alternative hypothesis, where the Y range is actually nested within the X range. So if you take a look at the observed samples, the 13 points we have, and you calculate from the observed samples, what you'll notice is that the range of X on the observed sample is greater than the range of Y. What you also notice is that the minimum of the X's here is 1.2, which is less than any of the values inside Y. And the maximum in X is 3, which is larger than all of the values that we observe inside Y. For part 1 of this question, you are asked to provide an analytic solution for the p-value of the permutation test. So instead of doing simulations or doing it numerically, what you're asked in this part is try to figure out analytically with a formula, what is the chance that we observe a t that's larger than or equal to the observed one we have. I have noticed that I have a typo over here. In hypothesis testing, we should do as extreme or more extreme. So we should also consider the equal case. This p-value should be the probability that t is larger than or equal to the observed value of 1.8. Okay, so in order to solve this question, let's try to understand what this probability actually implies. The probability that we observe a t that's larger than or equal to the observed value of 1.8 is essentially the chance that under the null hypothesis, where any permutation or partition of the x and y should be equally likely, the observed t, which is the range of x, exceeds the difference between 3.0 and 1.2. Now, or exceeds or is equal to this. But that's actually equivalent to saying that under the null hypothesis, or under any possible ways that we can partition x and y, what is the chance that we obtain a x partition, which we call x star, that contains 1.2 and 3.0? Well, why is that the case? That's because any other partition of x that does not contain the minimum of 1.2 and the maximum of 3.0 out of all 13 samples will not be able to give you a range that's equal to or greater than 1.8, right? That's the maximum you can attain. So essentially, you will need to find out what is the chance that you obtain a partition that satisfies these two things. All right. In order to figure out that, there are a few things that we consider. The first is how many unique partitions there are for x and y. We have learned this in the lectures. If we have a total sample size of 3 plus 10 of 13, we're going to choose 3 of them to be in x star and the remainder 10 in y star, then essentially the number of unique partitions is equal to 13 choose 3. Right. So these are all of the possible ways that we can partition x and y. In order to figure out this probability that's highlighted, we need to figure out of these 13 choose 3 unique partitions, how many of them are going to satisfy this? X star contains 1.2 and 3. There are only 3 observations inside S star, right? And this thing actually requires you to fix 2 of them. You fix the 1.2 and fix the 3. These 2 have to be inside X star, right? Then you have just 1 remaining element you can choose to be in X star out of the remaining 11 elements that haven't been selected. So essentially, the remaining element can be any element inside this list other than 1.2 and 3. So there are 11 possibilities, right? It can be 2 or it can be one of these y's over here. So essentially there are 11 ways to choose the last observation inside S star out of the 11 observations. Okay, so in other words, there are 11 ways to form a X star whose range can be greater than or equal to 1.8. So actually all 11 of those partitions X star are going to be having a range of exactly 1.8. And in this case, the analytical p-value will be given by 11 divided by the total number of partitions, 13 choose 3, which if you plug it inside R, so if we do 11 divided by choose 13, 3, we got something that's close to 0.038 as the probability. So that's the analytic solution. What we are going to do instead in part B is to use multi-kernel approximation to approximate this p-value. That might be what you're more familiar with when we were doing our lectures. How do you compute this value using simulations? Right, so first part of the code, we import the x and y data, which essentially are the vectors containing these 2 things. In the permutation test, first step is computing the observed test statistic. So the t observed gives you on this unshuffled original data, what is the range of x? Generally, you can do this by sorting x from the smallest to the largest. It's given by sort x and then you take the difference between the third and the first entry. That will give you the observed T. And then in permutation test, the next step is to generate a bunch of the permutation replicates of the test statistic on the shuffled data. Let's say we do a total of 999 of these randomly sampled permutations. Our Z, which is the concatenate of the original X and Y, is essentially a vector of length 13 that contains the X's followed by the original Y's. We're going to use the replicate function for 999 replications to obtain the permutation distribution of the range, right, the test statistic. In each replication, we are going to sample without replacement 3 out of the 13 indices, right? And we're going to say that the X star, which is the new partition of our X, so containing 3 shuffled X's, is going to be the entries in Z that correspond to the sampled indices we have. The remainder, which are going to be Y's, but our test statistic actually does not require us to have the object Y's, so we can save that. The J replicate of the permutation replicate of our range is going to be on X star, what is the range, which is the third entry of the sorted X star minus the first entry, which is the minimum. So that's what we're going to ask the code to return in each replication. And we should have a total of 999 of them, which are randomly sampled the test statistic under the shuffling of the original data. Third step in permutation test is comparing the observed value to the permutation distribution we would expect under the null hypothesis. All right, so one decision you'll need to make when you do permutation test is whether you do a two-sided test or a one-sided test. For this question, you can see that with the, say, the evidence against the null hypothesis is found when the observed T is greater than or equal to, I missed the equal to sign over here again, the observed value of 1.8. Right? What that implies is that we should do a one-sided hypothesis test. And that makes sense, right? We would expect the range of X to be larger than the range of Y. So we will want an alternative hypothesis that is consistent with that. We will want a larger T and or larger or equal T, that is, than the observed one of 1.8. So over here, we're going to do a one-sided hypothesis test where we look at the proportion of times out of the 1,000 replicates of the T, the range, including the original one we observed and the 999 on the shuffled data, what proportion of them actually were greater than or equal to the observed value that we got from the original data. And you can see that the p-value in this case is about 0.035, which is a little bit off from the analytic solution, but close enough so that they result in the same decisions. If you're asked to state what is your conclusion from the hypothesis test, make sure you know how to do that in this case. For this question, you will say we reject the null hypothesis that the X and Y follow the same distribution and endorse the alternative. All right, let's quickly run the code over here where we see what are the objects returned in each step. So to load the data, here's our X, here's our Y. So total of 13 samples. Observed T, we know is 1.8. It's going to be the maximum of X, 3 minus 1.2. B is the number of permutations we're going to do. Z is essentially the X's followed by the Y's. All right, so let's run permutation for one replication first. In each replication, we will first generate something called perm, which you'll see is going to be 3 of the indices sampled without replacement from 1 through 13, length Z. What essentially this says is that we're going to form a shuffled X star that contains these 3 entries of Z. 3rd entry, 13th entry, and the 7th entry. So this is our X star, and we will need to calculate what is the range of X star, which is our test statistic. You can see that it's going to be equal to 3.0 minus 2.1, which is 0.9. This is what we get. And essentially what that means is that in this particular partition, we actually did not achieve a range of X that was greater than or equal to the observed 1.8. So you replicate this for 999 times, you get a total of 999 of these TJs. Each of them is going to be the range that's computed on one particular version of the Y star. Essentially what we do here is that we concatenate the observed 1.8 with the 999 over here. And we look at the proportion of times that these 1,000 versions of the range was greater than or equal to 1.8. Shouldn't have printed this. And that's going to be our p-value in this case, right? Which is again quite close to what we expect given our earlier permutation, our analytical solution. All right. Are there any questions about this? Okay. If not, let's move on to the last question, which is actually what I think quite straightforward, but it's a nice review of Bootstrap and Jackknife. So the third question is going to ask you to work with the empty cars data inside R. And this data set, if you have taken a course on regression or machine learning, the professor might have used this data set to illustrate some kinds of like regressions that you can run to predict oil consumption of a car, which is given by a variable called MPG. That stands for miles per gallon, from various variables. For this particular question, we're going to fit a simple linear regression model where our predicted variable is going to be oil consumption, so MPG, miles per gallon, and the dependent variable we have is the weight of the car, which is given by a variable called WT, which stands for weight inside this data set. The regression line we have is that Y, which is MPG, is going to be some intercept plus slope times car weight plus some error term. All right. So when we were doing leave-one-out cross-validation, we learned that you can fit a regression line using LM, right? For this simple linear regression, we can just do LM of Y tilde X. And that will give you what is the estimated slope and the estimated intercept to this regression line. For this question, you are interested in figuring out what is the sampling distribution of the beta hat 1, which is the estimated regression slope. Right? Based on the observed samples, we want to do Bootstrap or Jackknife to figure out what will be a standard error estimate to this slope to the regression line, or what is a estimate to the 95% percentile Bootstrap confidence interval. All right, so let's get started with part A and B first, which both involve Bootstrap. You might remember from Friday's lecture or the earlier pages of this slide how you do bootstrapping. Essentially, the number of replications you do is usually it can be smaller, so something like 200 if you're just interested in estimating standard error. But when you're interested in some other things, like getting a confidence interval based on percentiles, it probably makes sense for you to use a larger B. For illustration here, since in part B we need to get the confidence interval, let's use a B of 1,000. You can use 2,000 too. All right, let's first load the empty cars data and specify that our predictor variable X is going to be the weight column inside this data set, and our Y is the predicted variable, is the oil consumption, MPG. In Bootstrap, what you need to do is to say, I'm going to do a total of large B Bootstrap replications. In each case, I am going to do a resampling of the original data with replacement. I'm going to draw a resample of size n, where n is the original sample size, with replacement. Using the resamples of x and y, we refit the regression line and obtain what is the statistic, in this case, the slope coefficient estimated from that resample. And at the end, we should have a total of large B of these bootstrap replicates. And then the standard error can be estimated just by the standard deviation of these B estimated slopes. So for this question, what we get for the standard error estimate is relatively close to 0.7. Let's try to run this part inside R and see what each object looks like. All right, clean my R window. Data mtcars loads a dataset from base R called mtcars. You can see over here that your sample size is going to be equal to 32. Right? What does that mean? It means that in each bootstrap replication, you're going to draw 32 resamples with replacement from the original data. Right? We only need the MPG and the WT variables inside this dataset. So let's say this is our X and this is our Y. So both of them are length 32 that contains the weight of the car and the oil consumption of the car. So the miles it runs per gallon. Our bootstrap number of replicates is 1,000. N is our sample size, right? In this case, it's going to be 32. It tells us how many resamples we need to draw. Just to give you an idea about the regression output on the full data. So if you use the full data to compute the what is the estimated slope, what you get is that the slope in front of car weight is about -5 point something, right? Meaning that on the full data of 32 observations, as the weight of the car increases by, if I remember correctly, 1 ton, you would expect a decrease of about 5.34 miles per gallon in that car's oil consumption, which makes sense, right? Because when your car gets heavier, then it's going to be less oil efficient in general. All right, so our beta 1 hat base here is actually a placeholder for storing our 1,000 bootstrap replicates to this estimated slope. Just since it's not very difficult, let's take a look at the full regression output over here. So if you do summary, it prints you a nice table containing the regression output on the full data. You can see that in this case, if you fit the regression line, actually both the intercept and the slope are significant over here, which means that the weight of a car is a nice predictor, is a significant predictor of the oil consumption. The estimated regression line in this case will be the predicted miles per gallon is equal to 37 something minus 5.34 times the weight of the car in tons. You can also see that here it gives you standard error estimates that are based on the asymptotic normal approximation. And in this case, if you use that, the standard error estimate of the slope is about 0.5591. But for this question, we're going to do that using bootstrapping to estimate that standard error. So in each replication, let's say b equals 1. We first randomly sample the indices. The i's over here are essentially saying that in this first bootstrap replication, I'm going to use these 32 rows of the original data, or the 32 x's and 32 y's. And you can see that these are samples with replacement, right? Because you see some duplicates over here. And then your beef bootstrap replicate of the beta 1 hat is essentially what you get from the regression output, where your y data are the resampled indices over here. So the 32 here, and your x are the 32 x's over here, right? And then again, we extract the second coefficient, which is the slope coefficient. And for this bootstrap replication, we can see that what we get is about negative 5.02 using that particular bootstrap resample. Right. So let's do this 1,000 times. Your beta 1 half B. You can see that it contains a total of 1,000 of slope estimates, each of them using a slightly different data set that's a resample from the original. Once you have this, you can get all sorts of byproducts. Right? For part A of this question, you get the standard error estimate. You can see that in this case, you can just take the standard deviation of these 1,000 bootstrap replicates B. And that gives you a standard error estimate of about 0.72, which is actually a little bit different from what you get from the regression output. All right, so we already have these, and part 2 is actually quite straightforward. In part B, you're asked to obtain a 95% percentile bootstrap confidence interval of the true beta 1, right? And in order to get this percentile bootstrap confidence interval, you can actually directly work with the 1,000 bootstrap replicates of beta hat B and find out its empirical quantiles. That will be given by the quantile function inside R, where you plug in the 1,000 samples you have, and you say, I want to look for the 2.5 and the 97.5 percentiles. Let's see what it gives us. Here it gives us that the 95% confidence interval based on percentile rank using Bootstrap are going to be negative 6.8 something to negative 4.1 something. How is this useful in practice? Well, in practice, it's quite useful for you to figure out, so once you have a confidence interval, does it contain 0? Right? And in this case, you can see that this interval is actually quite far from 0, very negative. Right? And what that tells you is that it's quite unlikely that your slope is 0. In other words, the weight of a car is indeed quite strong a predictor for the oil consumption of the car. All right. The last part of this question, again, asks you for the standard error estimate, but this time using jackknife. Let's recall that in jackknife estimation of standard error, we need to do that leave one out thing. We have a sample size of 32. For each I ranging from 1 to sample size 32, we're going to calculate a beta hat 1, which is the slope estimate, from the regression line, leaving out the ith observation. Right. So we're going to leave out one observation and work with the remaining 31. Use that to obtain the regression line and get what is the beta 1 estimate in that particular replication. Okay, so here's the code. The beta hat 1 jack is for storing the leave one out estimates. Right? It should have length 32. For each I between 1 and 32, we fit the regression line, leaving out the ith observation in the x and y, get the beta hat 1, and save that as the leave one out estimate to beta hat 1 in that particular replication. In the end, we can apply the formula for jackknife standard error estimation, which is given by the square root of sample size minus 1, so 31 in this case, times the mean of the square deviation between each of the LOO estimates to beta hat 1 and their average. And this will give us an estimate that's about 0.726, which you can see that it's quite close to what we got from Bootstrap. So let's quickly run this inside R. A bunch of zeros, I think. And then for each I between 1 and 32, we're going to store the ith entry. It's going to be a regression estimate that leaves out the ith observation. Right? So a beta estimate using 31 of those. All right, and then the jackknife estimate is essentially just spelling out what is the formula to that thing. Right? And that gives us something about 0.726. Here's a nice sanity check when you're doing jackknife. Results should be deterministic. For Bootstrap, it's sensitive to random seeds. For permutation tests, if you're doing the Monte Carlo thing, depending on your random seeds, every time the results someone gets to be different. But jackknife is deterministic, meaning that all of us, when we run the same problem, should get the same results. And when you rerun your code with a different random seed, you should also get the same result every time, right? Because jackknife is deterministic, meaning that we're doing this leave one out thing, where we're exactly leaving out a specific observation when we get each of the LO estimates. If you notice that you rerun your jackknife, you get a different result, that might indicate that something else is going on inside your code, and you should double check. All right, so that's it. Are there any questions about number 3? Or any questions in general?